Okay. So fine, let us start. So today actually is the first class for the EMTL topic, and this is actually one of the very important topic. And many people feel that this is a tough topic, but ideally this is not a tough topic, right? So electromagnetism and the transmission line. So both the topics together. So this is electromagnetic fields and the transmission lines. Right? And this topic actually is even useful in the case of the power systems as well, right? In case of power systems, actually, so long transmission line, right? So long transmission lines, actually, the concept actually is exactly the same concept what we are going to discuss in the context of the transmission lines, right? So the transmission lines are discussed in two different categories. One is actually the wave propagation type and actually the current propagation or the voltage propagation type, right? So these are the two variations actually that we will be discussing. The wave propagation actually mainly in the concept of the electromagnetic fields and the transmission line. So that is specifically when there is a wired transmission of the electric waves. So maybe a voltage wave or maybe a current wave, when it is getting transmitted, that will be analyzed in the case of the power systems. But the concept is exactly the same. Got it? Right? So, and this is what we are going to discuss it. And the first, actually, we will be discussing certain aspects. So one is actually, this is being the first class of this EMTL. So what is the syllabus? And the second one is, what are the books to be followed? And the third point is, right, approximately how many number of hours? Right? And so just actually have a feel of the previous year questions. Right? So all these things actually I'm going to answer it now. And if you have any questions, actually I will add it. You can let me know. Right? And we will clarify all those things. Then we can actually start off the topic. Right? Anything you wanted me to add for this? Great. Right? Okay. Now let us start. So first actually let me list down the syllabus. Right? So Maxwell's equations, wave propagation in bounded media. Wave propagation in bounded medium. And boundary conditions, reflection and refraction of plane waves. Plane wave. Reflection and refraction of plane wave. Transmission line, traveling and standing waves, impedance matching, Smith chart. Transmission lines. Transmission lines. Traveling and standing waves. impedance matching Smith charts. Right, so this is the complete syllabus what we are going to discuss as part of this particular topic, right? And then actually to add to this, actually there is one more question. So what is the weightage of this topic? Right? Okay, so let me answer one by one. So in this case, actually the first thing is actually the syllabus. In case of syllabus, actually we have Maxwell's equations, wave propagation in bounded medium, and boundary conditions, and reflection and refraction of the plane waves, transmission lines, and traveling and the standing waves, impedance matching, and the Smith charts. Right. So this is the complete syllabus what we are going to discuss it. But one important point to note is, so to understand the Maxwell's equations, we will have to understand electromagnetic fields as well. Right. So the electromagnetic fields actually we will be discussing it first, though actually it was not part of our syllabus. That needs to be understood fundamentally to understand the Maxwell's equations. And Maxwell's equations are used to derive the wave equation. So that's why actually Maxwell's equations in all the formats, maybe the differential format or the integral formats, the four Maxwell's equations actually, we will be understanding everything. And the derivations of the Maxwell's equations lies with the electromagnetic fields, right? So that's why actually we will have to understand the electromagnetic fields as well. And then actually, so we will be deriving the wave equation from the Maxwell's equations, and that wave equation actually we will be analyzing in different mediums. So in bounded medium and unbounded mediums, we will be discussing it. And on top of that, actually, so that wave, whatever is going to be generated with the electromagnetic fields, that will be analyzed in case of transmission lines, right? So that actually we will be discussing in the context of the transmission lines. And then actually the maximum wave is getting transmitted without having any reflection in case if there is an impedance matching. So that impedance matching technique actually we will be discussing it along with this, all these concepts. And then actually, so traveling wave and the standing wave. So all these concepts actually at +2 standard, whatever we have learned as a wave equation, that wave equation actually is discussed in multiple contexts. So here actually, this is specifical to electromagnetic waves we are going to discussing it. So in +2 standard, whatever we have learned as a wave equation, that is in general for any kind of wave, maybe a mechanical wave, maybe electromagnetic wave, or electric wave itself, or the magnetic wave itself. So that is valid for all the contexts. So here in our context, it is the electromagnetic wave we are going to discuss it. Got it? And then actually the Smith charts actually, so we will be finding out certain values with the help of this Smith chart. So this actually you have to understand this Smith chart based on the impedance value or the per unit impedance value. We will have to understand the reflection and the refraction coefficients. So those things actually, this is a graphical technique which we are going to use it. But understanding this Smith chart actually is not that easy, because actually you have to know the internals of this, right? So that internals actually everything we are going to discuss as part of this transmission lines, right? So this is the complete and simply short syllabus. It's not a very high syllabus. This is actually very small syllabus. But the thing is that understanding this concept, it involves a lot of mathematical aspects. That's where the problem lies, right? You have to be pretty good with the vector calculus. So pretty good, like actually you should be excellent in vector calculus. Then only you will be able to understand this particular topic. Otherwise, actually it will be very tough for you. But don't worry. So I will be explaining all those basic concepts, and then actually we will continue with this particular topic. So I will be dividing this into 3 different sections. One is actually the basics. So basics actually it involves the mathematics. And the second part actually is the electromagnetic fields. Right? And the third context is this particular one. So this is whatever the syllabus we have discussed. So this is the transmission lines aspects. So transmission lines meaning it is involving all the syllabus of our. So this third part is actually the entire syllabus what we have it, right? And this is the summary of what we are going to discuss it. Got it? And this basics actually involves 2 different concepts. One is actually the coordinate systems. And the second one is the vector calculus. So these things actually you have to understand very well. And then actually the automatically electromagnetic fields actually very easy to understand. And based on these two concepts, actually, we'll be understanding the Maxwell's equations, and Maxwell's equation continues for the transmission lines. Got it? Any questions? Right? Any questions on this? Right? Okay. And then actually, so this is what are the books that needs to be followed, and we'll be using only one book, and that is pretty good book. That is Electromagnetic Fields by William Heath. Right? Electromagnetic Fields by William Heath. I will show you that book, and that book actually you will have to follow. So the outside appearance may be different. So this is the book actually I'm going to follow, but this I bought it actually long back. It was somewhere around 2001 or 2002, and I'm using the same book. But actually nowadays actually you might have found actually the latest versions of the same book, but this is actually very good book. So you can understand very easily this particular book if you are good with the mathematics. Got it? So this book you can buy, and this book is valid for all the topics what we are going to discuss it. Got it? Right? Okay. And then actually, so this one, so approximately how many number of hours actually we are going to take it for this? So I think somewhere around maybe I'll be taking up around 25 to 30 hours. Right? 25 to 30 hours actually I will try to finish this particular topic because this syllabus is short. And then actually, so approximately how many number of hours and what are the books that needs to be followed. So all these things actually I have answered it. And then actually have a feel of the previous year questions. I'll just show you what are all the previous questions that were asked earlier. And based on that, we will have an idea. So what we are going to discuss it. Right. So this is actually 2019 paper. And two extensive homogeneous isotropic dielectrics meet on a plane at Z is equal to 0. For Z greater than 0, epsilon R1 is 4. And for Z less than 0, epsilon R2 is 3. A uniform electric field E1 is equal to 5AX cap and minus 2AY cap plus 3AZ cap kilovolts per meter exists for Z greater than or equal to 0. So find E2 for Z less than or equal to 0 and the energy density in joules per meter cube in both the dielectrics. So this is actually a simple question and very short question for 10 marks. And this is actually the wave propagation and the reflection and the refraction concept. And this will be straightforward. We have the derivations and we will do all those derivations, and based on that we can substitute this and we can get the values of these electric fields and the magnetic field. So this is an electric field. So for the same electric field, reflection and refraction actually we will have to identify. And then actually so energy density also actually we will be calculating it for the electric, right? And a lossless line has a characteristic impedance of 50 ohms and is terminated in a load resistance of 75 ohms. The line is energized by a generator which has an output impedance of, right, which has an output impedance of 50 ohms and an open circuit output voltage of 30 volts RMS. The line is assumed to be 2.25 wavelength long. Determine the output impedance, the magnitude of the instantaneous load, and the instantaneous power delivered to the load. So these are all the things actually that he asked us to calculate. And all these things actually straightforward related to the transmission lines, right? So this is a straightforward question. All these kind of questions that were discussed in the William Heath textbook, and we will be solving all those questions in the class also, right? So a two-dimensional electric field is given by E equal to x square AX cap plus x into AY cap volts per meter. Show that this electric field cannot arise from a static distribution of the charge. So this is actually, you have to prove that actually this is not going to be generated by a static distribution of the charge. So if the charge is continuously changing, then only actually this can be coming out, right? Because actually this is a variable field. So variable field is going to be generated with the variable charges only. Static field is generated by the static charges. So that actually he asks us to prove. And a transmission line of length 5 meters is tested at a frequency of 20 megahertz. And when the far end of the line is short circuited, the impedance measured at the sending end is 4.61 ohms. And when the far end is open circuited, the impedance becomes 1390 ohms. Calculate the characteristic impedance and the propagation constant of the line, right? So this is also straightforward, a long transmission line concept. The same concept actually it will be there even in the power systems also. The same thing is discussed even here also. So, but here actually we will learn in deep, but power systems actually we touch only the peripheral nature. So here actually we will learn the transmission lines to a deeper level. And an aeroplane flies over the surface of the ocean, for which sigma is equal to 4 Siemens per meter and epsilon r is equal to 81 and mu r is equal to 1. The aeroplane transmits the signal in the form of 1 megahertz plane wave having an electric field intensity of 1000 volts per meter and propagating vertically downward. If a submarine requires a minimum signal of 20 microvolts per meter for adequate reception, determine the maximum communication depth of the submarine, right? So this is actually a practical application. So this one actually, so from the aeroplane actually, he wanted to transmit the signal to the submarine which is there in the ocean, right? And with what strength he need to transmit the signal so that actually the submarine will receive it. So submarine actually it will have actually its own ability to receive the signal, that is actually 20 microvolts per meter. If it is available as electric field, then only actually it can receive. And the same thing actually at the top of the aeroplane actually it will be delivering with 1000 volts per meter, but it is receiving 20 microvolts per meter. So in between actually there is a huge gap, and there is an air over in between and there is a water also in between. So, and obviously actually these mediums whatever is present in between, they are going to so they actually subsidize. That means actually they will reduce the strength of that particular signal. By the time it reaches the submarine actually it has to be minimum of 20 microvolts, then only actually it will be useful for us. Got it? So this actually is a practical application. So these are all the kind of questions. And if you notice, all these questions are actually just based on the transmission lines and the wave propagation. That's it. All the questions, right? And then actually we will see in the 2018 paper, we will see. So in 2018, so a low loss transmission line has characteristic impedance of Z0 is equal to 70 ohms and is terminated by another impedance of 115 minus J80 ohms. The wavelength of the line is 2.5 meters. Find SWR, this is the standing wave ratio. So you know that actually standing wave ratio is going to be calculated at +2 standard also. The same concept actually we will be using it here, but the standing wave ratio may be complex numbers also. So we will be discussing all those things here. And maximum and minimum line impedance, so Z1 max and the Z1 minimum, and this needs to be calculated. And if the input impedances of a short and open circuited transmission line of length 1.5 meter is ZSC is equal to minus J78 and ZOC is equal to minus J90 respectively. Determine the characteristic impedance Z0 and the propagation constant gamma of the line. If you notice, there were two questions actually just based on this particular concept, that is the Z0, that is the propagation constant, and the characteristic impedance actually that needs to be calculated. In 2019 also it was asked, and 2018 also it was asked, right? And third one is derive the Maxwell's equations of a time varying magnetic field based on Ampere's circuital law. And a parallel plate capacitor with plate area of 5 centimeters square and plate separation of 3 mm has a voltage of 50 sin 10 cube t volts applied to its plates. Calculate the displacement current assuming epsilon is equal to 2 times of epsilon naught, right? And this actually is a straightforward question. And if you notice, it was not part of our syllabus. So Maxwell's equation actually it was started, but Ampere's circuital law, it comes before the Maxwell's equation, but actually this proof was based on the Ampere's circuital law, right? So that's why actually electromagnetic fields, though it was not explicitly mentioned, Maxwell's equations were derived from those. That's why actually they will be asking the questions from there also, even without actually specifying in the syllabus, right? And a traveling electric field, right? A traveling electric field in the free space of amplitude 100 volts per meter strikes a perfect dielectric as shown in the figure, right? And determine the value of so that is ET. So there is the value actually that is going to be mentioned here. So this is E1 and this is ET. In between actually there is a dielectric with an epsilon r is equal to 20 and mu r is equal to 1 and sigma equal to 0, right? And this is actually the transmission line concept only. And a uniform plane wave is air partially reflects from the surface of a material whose properties are known. Measurements of the electric field in front of the interface region yield a 1.5 meter spacing between maxima, right? With the first maximum occurring 0.75 meters from the interface, a standing wave ratio of 5 is measured. Determine the intrinsic impedance eta W of the unknown material, right? So this actually, again the standing wave ratio concept. So that's actually standing wave concept actually we will have to understand clearly, and where actually there are crests that are sequentially appearing and there are troughs also sequentially that are appearing, and between them actually how much is the distance that decides actually how much is the amplitude, so that is the wavelength of that particular wave. So all those things actually we will be discussing, and here actually is such kind of question. And this is in 2017. Show that for a distortionless transmission line, the attenuation constant alpha does not depend on frequency, whereas the phase constant beta depends linearly on it. So this actually show that a distortionless transmission line, the attenuation constant alpha does not depend. So this is actually the derivation of the wave equation. So in that actually we will be proving this. So this is just the derivation of the wave equation from the Maxwell's equation. And then actually the second one is what is meant by an infinite transmission line. Also explain the term electrical length of your transmission line, in what units actually it is going to be measured. So this is a theoretical question, right? So the basic concept we need to understand, we will have to discuss the theory here. And determine the electrical length of a 20-meter long transmission line operating at 1 megahertz. And if mu is equal to 0.7 c, so u is actually the velocity of the wave, which is 0.7 times of c, where c is the light velocity on the line. Take c is equal to 3 into 10 power 8, right? So determine the electric length of a 20-meter long transmission line. So this is actually the same previous question whatever is discussed, right? So that is the extension of this. The electric field and the magnetic field in free space are given by E is equal to 100 by rho cos of 2 into 10 power 7 t plus beta z. And so this is actually h is equal to h naught by rho cos of 2 into 10 power t into t plus beta z. And both are actually exactly in phase, if you notice, right? And express these fields in phasor form and determine the constant h naught and beta such that these fields satisfy Maxwell's equations. The permeability and permittivity of the free space are 4 pi into 10 power minus 7 henries per meter and 8.854 into 10 power minus 12 farads per meter respectively. So this is actually h and mu l set that were given, and express the fields in phasor form. So these things actually we will have to express in the phasor form and determine the constant values of h naught and the beta value such that these fields satisfies the Maxwell's equation. So basically we will have to use the Maxwell's equations and use these values, identify this h naught and so this E value. So h naught and beta value based on this. Got it? So Maxwell's equations and the wave equation will help in deriving those values. So I think so maybe actually we can stop. See this. So finally actually if you wanted to notice what are all the questions actually that are discussed in this case. One is actually the wave transmission line. So wave propagation in different medium. That is one concept actually that was repeatedly asked. And then actually the transmission line concept and the impedance matching concept. So this is also actually it was recurrently that was asked. And then actually Maxwell's equations in deriving, so basic derivations of the Maxwell's equations as well as application of the Maxwell's equations to derive the wave equation. In that context actually he asks us certain theoretical questions as well as certain models of the problems. Got it? So this is the complete syllabus actually. So what we are going to discuss it, and these are all the previous questions. I hope you got what standard we need to be preparing for this. If you notice, all these questions are actually not that easy if you carefully notice. So these questions are actually a little tougher only. It involves a lot of fundamental concept that you need to be understanding. Then only you actually understand what he is asking for, right? It's not like circuit theory where actually you can straight away understand everything properly. But here it needs a lot of background. So that background actually will decide whether you are able to understand the topic or not. So what is that background is? So it will be a sequential build-up of the background. Actually, I will do it, and that is starting from the mathematical background, that is the coordinate systems and the vector calculus, and that extension leads to the Maxwell's equation derivations, and the Maxwell's equation derivations will be used in the wave derivation, and in the wave derivations actually you will get all these concepts. Got it? If I straight away start with the wave equation or the Maxwell's equations, nothing you can understand. Got it? Any questions? Right, so I have discussed all these concepts and then actually have a feel of the previous year questions and what is the weightage of this topic. So this is actually most of the times 50, sometimes actually 60 marks that were given, right? Most of the times 50 and sometimes it's 60. And actually we will see one more concept. See this, so suppose actually if you notice the questions actually, right? and this is actually 2019 paper. Okay, look at this one. So this is actually the EM theory portion. So EM theory actually question number 1 actually 10 marks, question number 2 10 marks, question number 4 10 marks, and question number 6 20 marks. If you notice what you can notice here. So 5, 6, 7, 8 this is from section B, and 1, 2, 3, 4 for section A. Now if you notice EM theory, it was asked in question number 1, 2, 4 and 6. That means in any section actually the question can be asked. That is one thing. And then actually you cannot simply leave the preparation of this topic being it is a tougher one, just because of the reason that the questions are actually, every question actually there is a touch. Every question you can notice that actually there is a question, except for the question number 3 in section A. Everywhere actually you can find a question, and even section B also you can find a question for 20 marks. And we will notice this one also. See this. So in this case actually section A 20 marks and section B 30 marks. So total 50 marks in 2018. Out of that actually question number 2 is for 20 marks, and question number 5 is for 10 marks, question number 6 is for 20 marks. So that's why actually it is there both in the section A and section B. If you notice in 2017, you can see that actually 10 marks for question number 1 and 20 marks for question number 2, and then 20 marks for question number 7, total actually 50 marks actually that was given here. And 2016, if you notice, this is 10 marks in question number 1, and question number 3 20 marks, and question number 4 30 marks. Total 60 marks was given, but only specific to only section A. So no section B questions were given here. But if you notice, all these questions are distributed. It's not given for a single question. So that means actually many people think that actually I leave this topic and I will just lose only 10 marks, which is part of the compulsory section of question number 1. But in reality, it's not. Got it? So that's why actually you cannot take this as a choice. Questions you have a choice, but the topic you don't have a choice. And in 2015 also you can notice that actually 10 marks in question number 1, 20 marks in question number 3, and so only 30 marks that were given in 2015. That means actually the weightage was actually increased nowadays for this particular topic. Got it? Any questions? Any questions on this? So I have not updated 2021, right? So 20 and 21 actually I have not updated, but more or less actually it will be similar only. So if I find time actually I will update those questions also, but it's okay, right? But you can exactly assume that this is the similar kind of, so maybe 50 or 60 marks and the questions will be distributed and the same syllabus. Got it?